And so the first figure that we're going to be making is a heat map. And so heat maps can be used to show a lot of different things. You can look at the variance between samples. You can look at the most, like in our paper that we looked at, we saw that, they had a figure with a heat map. And the first figure with the heat map was really just showing that there are differences between samples visually. And so we'll look at that now. So first we have to create a normalized set of data. Heat maps always need to be normalized because of the way that they show the data. So first we create that, and then there's some options here. So you have 3 options. In a heat map, you can either show all significantly differentially expressed genes. This gets a little big, right, because we have quite a few significantly expressed genes. We can see how many we have by just taking this in row part of this percentage calculation that we left off the last video on. And we have about 1,000 genes. So you could make a figure with 1,000 genes, but that's going to be a little hard to see. But it might help you assess the differences in just the samples. We can also make heat maps of the most, the top most significant genes. We could also make, a heat map of the genes with the greatest absolute fold change that are significant. So genes that are already significant, but they have greater differences in expression between our non-cancer and our cancer samples. So you could use heat maps to show several different things, and there's code for all 3 of these. And so those are what's described here in option 0, 1, and 2. So option 0 would be if you want to make all significant genes. And to make figures, I need to reframe my Rstudio just a little bit because I need this panel where the plots are going to print to be a little bit bigger. So I'm going to move this over. I'm going to move this up to the top. And I'm going to click on plots here just to get ready to see those plots. So the first one we'll do is just all of the significant genes. And you're welcome to choose kind of whatever you feel most comfortable, whatever you feel able to best talk about in the report. So first I can do this, and then it says if you comment out line 198. Right here, I think I've moved it down one, so it's commented a little bit more. Commenting something out just means adding this hash symbol in it so it's not running. So if you run this, you can actually ignore these other lines for now. Actually, it's really that this needs to be commented out, this norm sig, because we're naming something up here norm sig. So we're kind of swapping out options here. So if I just run this, then I can come all the way down. I can ignore all this for now. I do need to run this data frame. And then this heat map command is going to be running on the norm sig. So the first one is just going to be all genes. So hopefully this won't crash my Rstudio. It's pretty kind of computationally intensive to show a lot of genes. But that's what we see here. So we can see that the gene names are written, but we can't even actually see them. We can use the zoom button to open it up in another window. But honestly, it still doesn't help us much. What we can see here and what we want to see here is that there are differences between our non-cancer and our cancer condition. You can see here that the patients are labeled by color and the conditions are labeled by color up here as well. Each row in a heat map represents a single gene. So these are basically evaluating the expression levels, the normalized expression for a single gene across all samples. And you can see this kind of phylogenetic tree looking thing on the left. This is because it's a clustered heat map. So I have that turned on here, true. You could turn it off with false if you didn't want the tree. But this just clusters genes by their expression patterns, and it helps us see kind of blocks of patterns in the data. It's not letting me zoom. Let me. So what we're looking for here, when I mean blocks of expression patterns, we see this big blue block in our cancer sample. And we see another big blue block down here, and then we see these redder blocks on the corners. So here it's showing for all of these genes, there's patterns of slight underexpression. So blue right here is underexpression. 0 would mean, kind of equivalent expression between cancer and non-cancer. And 2 is going to mean, and redder is going to mean higher expression. So this first block shows a block of genes that are underexpressed, slightly underexpressed in cancer condition, and more expressed or sometimes overexpressed in your normal condition. What you wouldn't want to see in a heat map would be a totally random pattern. If just every gene were totally different between samples and between conditions, then we might be concerned about the integrity of our data, our samples. But this is what we want to see. We want to see blocks of patterns. So this again doesn't tell us that much besides the samples are different, the conditions are different. Okay. So that is the heat map of all genes that are significant. We can instead recomment this, so ignore this line, and go to option 1 and make a heat map of only the top insignificant genes. So here I will run this command. It runs it right here. Also note that if you use the key command, or even run, it'll just run the next line that's not commented out. So if I hit this run, it just runs this line, even though my cursor wasn't necessarily on it. So here I need to uncomment this norm sig because we actually want that to be here because we're not using the one up here. So I'm going to do top in here, and you can change this number to show however many genes you want. So let's just look at these 25 for now. So again, we just run all of these lines up to the heat map again, and now we can see a much simpler heat map that shows only the top N genes by their significance. So these are the most significant genes. And you can see that we also have kind of these clustered blocks of patterns, this overexpression, underexpression here. So this would be a great plot to pick out some genes of interest. So for the report, as always, I recommend talking about overall patterns that you observe in your data. And I think that for RNA-seq analysis, often what we're interested in is, what are these genes? Biologically, what are they doing? Can we connect that to the conditions that we're looking at? So, is this GLY-ATL gene, since it's upregulated in the cancerous conditions, does it have, maybe it is... maybe it is an oncogene that's being upregulated and causing more expression, more cell growth. So I don't necessarily know that that is, but I'm saying you can look these genes up on databases like UniPro or just Google the gene names and try to find out kind of about the biological function of them and talk about a couple of genes of interest in your report. And when you're talking about individual genes, remember to make sure to tell us both the p-value, the adjusted p-value, and the fold change when talking about individual genes. And at the very end of the script, there's an option to make plots for single genes just to show those expressions. So we'll get to that as well. So that is just by significance, but if we wanted the ones that are most differentially expressed, we can also use option 2. So I'm going to comment this in and uncomment this. So now instead of running this sorted DE variable, I'm creating another one here that focuses on fold change rather than just p-value by itself. So I can run that here, and again, I just keep running the same lines down to norm sig until you can see that it changed. So let's look at this one. So these are our most differentially expressed genes. Oops. And it's kind of interesting, we should see more consistency between the samples, to be honest. It's a little concerning we don't. That, is kind of involved in the quality assessing of our data, which we didn't really spend time on here, but I'll share a link about that quality assessment in the video notes and also on Discord. So these are showing very differentially expressed genes, and they're looking not very consistent between, samples within the same condition, which, like I said, is concerning, but we're still going to go with that. So you could pick out some of these genes and talk about them as well. Just make sure when you represent a heat map in your report that you tell us in the legend what data that's based off of, right? So is it all genes? Is it only genes by p-value? Is it only genes by fold change that are significant already? Tell us more about it in the legend. So that's our heat map. So next we can move on to MA plots and volcano plots. So y'all have seen a volcano plot in the paper that we read. And MA plots are just a slightly different version of that show the expression values as well. So I'm not going to explain too much of this, except that I think I have inconsistent p-values in different places. So I'm going to change this to 0.05, just because elsewhere in the script I used 0.05, which is a little more permissive than 0.01. So I'm just changing these. Again, make sure in your report to tell us what threshold of significance you're using. And in these plots, this is kind of what's setting up is what we're labeling as significant. So you want to tell us what this p-value, this adjusted p-value is in your paper, in your figure legend, everywhere you can. So we're going to run this. I'm running some more stuff. And now the first one we're making is a volcano plot. And it's going to color our significant genes green. Oh, right. I'm just sitting here. So I sent it to a variable. I stored the plot as a variable instead of just printing it by itself. So you have to run this as a name to get it to show, because it's saved as a variable, as this volcano variable. And you can see that this is a little hard on my little computer, so I imagine that many of us will run into kind of issues with that. Rstudio crashes sometimes, and hopefully we won't happen too much. See, nothing was popping up here for a minute, and then finally it did. I'll also show you how to export figures and resize them, because with the heat maps you saw that in this little window it sometimes compressed them so that we couldn't see the gene names. Similarly, what's happening here is that all of these are going on top of each other and it's just a mess. So we need to expand this plot a little bit before we can save it. So I can do export, and then you can do save as image. And usually it lets you resize it before it actually saves, but I'm often saving to a PDF, so I'm not totally sure how this is going to work. Oh yeah, you can. So you can name the plot here. You could probably save it as a JPEG, just because that's probably what's easiest to go into the document. But you see this is still a little cramped, so I might need to raise the height a little bit. So I can reset that and say update preview. And sometimes the preview just doesn't update, which is really annoying, but just something we deal with. So a good idea to deal with that is just to try to make it bigger than it already was. You could say this view plot after saving. So if I do this, it'll pop up. So I'm just going to say test MA plot here. And let's take a look at that plot. So it may take several iterations of saving them with different sizes just to make sure that the figure is clear. It's important that the figures are readable. So right now, as you can see, it's still not readable. Of course, there's going to be some amount of overlap, but we want to probably expand the figure just a little bit more. But for now, let's actually talk about the figure and what it means. So the volcano plot, as y'all have seen already, on the y-axis shows the adjusted p-value. And it's in a negative log scale, so higher numbers mean lower p-values. So the most significant genes up here we see are FLNC, this GlyATL, F5, ones that we've already kind of seen coming up in our heat maps. So all of the green dots, every dot on this plot represents a different gene. But all of the green dots are ones that are significant based on that threshold that we set on this line. So if you change that, to 0.01, you'd have less green dots just because that's a more stringent cutoff for significance. So what we can do with these plots is we could talk about global patterns, right? So we're getting used to thinking about discussing our data in terms of larger patterns and focusing in on smaller patterns. So the larger patterns that I first notice here is that it looks to me, just visually, that there's more significant down-regulated genes than up-regulated genes. So that's kind of a general pattern you could mention. And then you could talk about specific patterns. So that's where I would then start choosing individual genes to look at closer, look up their biological functions, see how they work. So the volcano plot, again, shows the adjusted p-value on the y-axis, and on the x-axis, it represents fold change. So this 0 means no difference, right? The negative means down-regulated genes. So this FLNC gene, as we saw in this data frame, if I look at FLNC, we see that it's a down-regulated gene. It has a negative fold change, which means that it is lower expressed in the cancer samples than in the normal samples. So this is a downregulated gene. So maybe, I don't think this is actually what FLNC is, but we talked about oncogenes and tumor suppressors. What if FLNC was a tumor suppressor and it was downregulated in cancer and not doing its job suppressing tumors? So that's the kind of, thinking about the gene's function that I'm talking about. And over here we have overexpressed genes, so genes that